for today I want to show you some numerical study of heterogeneous interface in dynamic cracks. And if I first show you a bit the length scales of what you're looking at, here I'm talking about shear crack. And because I show you this here is actually, most of the times I'm thinking about friction. So how something starts to slide. And there is some propagation going on, like in earthquakes over here, that resembles very much shear cracks. And so there is lots of cases where you can actually show it's the same behavior, and that's what you're looking at. So excuse me if I say slip front at some points, I actually mean shear crack in this context. There's different length scales that happen in these frictional interfaces, so the shear cracks from very large scale down to nanoscale in nanometers. What I show you today is more in this size of range, where we have laboratory experiments with 2 blocks in the centimeter to meter length scales. We have some area in mesoscale that is incorporated in this cohesive approach. But whatever I show you here actually has also some validity for this length scales here. The smaller length scale is just not part of the phenomenon that we are actually looking here at. So I'm sure most of you know that already, but I want to bring everybody on the same page. So there is a question of SubRayleigh and super-shear crack growth. And if you take a crack, a shear crack, that is hitting at some point because you have some local phenomenon happening, you usually have propagation that starts at this point. And so I'm showing here propagation speed along the position, and you have the Rayleigh wave speed of the material, the shear wave speed of the material, and the P wave speed of the material. So in very typical case, you have propagation going from here, and here everything is uniform, material properties, loading, everything, the easiest of all cases. And so you have propagation that goes up and approaches the Rayleigh wave speed. That's called SubRayleigh behavior. Now, if you take fracture mechanics, linear elastic fracture mechanics, the basics, and you take an energy consideration, which is the underlying physics of the fracture mechanics or linear elastic fracture mechanics theory, is you compare released potential energy with fracture energy in order to ask yourself, is my crack propagating? Okay, what is that actually? What it actually means is fracture energy is kind of material property or interface property, depending on whether you have a weak interface or not. We do have a weak interface. We have a frictional phenomenon. And then on the other side, you compare it with the energy that you have available, which is this released potential energy that depends on many different things like the geometry, loading configuration, crack length, and material, and so on. Now, if you compare those lengths and you do the statics, you can see if you have propagation or not, but you actually can do dynamics as well. And if you compare those energies, it tells you that you have energy dissipation at the crack as long as you stay below CR. And as soon as you have CR speed, you actually have 0 energy dissipation, which is physically a little problem, and especially if you get in between the Rayleigh wave speed and the shear wave speed, your crack is emitting energy, which is physically inadmissible, and that's why this area is often called inadmissible area. Okay. Some later research has then shown that you can have propagation in super-shear if you assume that your crack is not a singular crack, but you have a cohesive zone, and so it's possible over there. And so for a long time there was a question whether how can you have a crack that propagates here and then suddenly is super-shear going through this inadmissible area. And that was a mystery for quite some time, until some really amazing paper in '76, a numerical study where Andrews looked at a shear crack propagating. So what you see here is basically, this is the crack here. Here you have this is the small cohesive zone, very thin in this area. This is actually the opening shown in this direction, but it would be more too. And in front you would have the stress concentration. And what you can see here is there's a little bump. This bump comes due to the acceleration, to the initial initiation. And if it propagates, and what you see here now is space, time, Okay, the crack initially is over here. This is intact area. This is the cohesive zone here. This is the initial crack, and then it starts, because it's just above the critical length, it starts propagating and approaches the Rayleigh wave speed. So this slope here represents Rayleigh wave speed. You see that the cohesive zone is detracting as it is it should with linearized fracture mechanics. Then at the same time, this bump ahead is actually propagating, and this bump is propagating at the shear wave speed. You see the slope here. And at some point it reaches a critical load and causes a dollar crack, as it is called, and this dollar crack then allows transition to super shear. So this is the mechanism that was discovered with numerics in '76 that allows you to jump over this inadmissible area. Now, it took almost 30 years until experimentally it was observed that this is the group of Rosakis at Caltech, where you have, this is from the side, photoelasticity used. You see the interface here. They nucleate a crack somewhere, a shear crack somewhere in here, and then at some point here you see that the crack is over here. You have the fields, the S wave, and at the later point suddenly you have the Mach cone here, and so you have super shear propagation. Now, just as a little aside, I won't go into details. Actually, just very recently, we are collaborating with Jay Feinberg's group in Israel. We have used numerics to look at this bump, and we're able to actually figure out what you have to look in the experiments to trace this bump. And now this is the results of this paper. So this, not like here where we see from the sides, here we see again space time, so it's kind of the same behavior here. You have an initial crack that is starting here, some slow nucleation, propagation going on. The cohesive zone is very small and you cannot really see it with this area here. But at the same time, we were able, with this information from the numerics in the experiments, to track this little bump. And these are the black dots. We could measure it's the shear wave speed, and then here you see the dollar crack that is propagating. So actually this is very new results that closes this gap of the missing bump that wasn't able to be observed in this methodology. Okay, this is just as a little side. The important thing is this bump, because for what I'm showing you now, it's an important aspect. Now, if you consider a system that is uniform loading, uniform material properties, homogeneous, everything perfect, you actually can determine, or in this paper, this Andrews paper, you could determine at which length you have the transition occurring. Now, it's a bit a strange graph for those who aren't used to it. It's inverse relative shear load, so high load would be here, low load over there, and inverse transition length, so short length over here, long length over there. But basically what it says is if you have a very highly loaded area, you have a transition from SubRayleigh to super shear, so you're coming down here at a very short length, so it's intuitive, okay? But it actually, you're capable of defining the length for a given state. You know your loading, you know your properties, and you can determine at which length you should have transition. Now this transition length, it scales with the fracture energy at the interface, it scales with the elasticity, the stiffness of the material, and it scales with inversely to the stress drop squared of the interface that you have. Okay? Everything uniform. Now let's get to the interesting thing. So this is the assumption. Everything uniform. Uniform properties, uniform loading. Now, uniform properties, uniform loading, uniform interface properties, that's not the situation in most realistic systems. And now we have to figure out how actually you can have this heterogeneous affecting this behavior. And that's what you're trying to look at here. We have a three-dimensional setup. This is finite element simulations. It has millions of degrees of freedoms that we use in order to be sure that everything is mesh converged. We simulate two blocks. So the top block is this block over this length. We have a bottom block over here. What is in color is the interface between the two blocks. It's infinite in this length, so out of, like this area, infinite. The loading looks a little bit weird, but what we do is we have a finite system, but the loading is applied so that we have uniform loading in the finite system. Okay, so we don't want to look at the difference in loading. We have uniform loading along interface. And then we have some notch and some propagation going on, and if everything is uniform, you have some flat shear crack that is propagating over there. Now, material properties is of the order of polymeric material, which is a material that is often used in experiments. Nothing special. Now, if we look at the interface, so this, when I show you this from now on, this is space. It's basically a slice of this interface because it's periodic. It's infinite is in this area because we wanted to avoid to have these edge effects, to really understand the fundamental underlying phenomenon of the heterogeneity. So what we see is basically this stripe out of here, this length, this width, and here this is the property is all the same. We have some linear slip weakening law, as we call it in friction. For fracture, it's basically linear cohesive law, nothing special. It is a non-zero reference level, but it doesn't matter if you normalize everything out. This has absolutely no effect of the results. It's the same thing. The material properties is fracture energy that is like this. It's a weak interface. Actually, for a weak interface, this is pretty high. I do it so that we have mesh converged results, but what I show you in the end is actually independent of this. I can show you that we have a length scale and a non-dimensional length scale that we can use to describe everything. So you could scale down everything to a smaller scale if you want. Now, what we study is one case where we actually go and change the interface properties to some weaker areas that have, like, for example, 10 joules per meter squares, and we organize them in stripes like this. So you have an initial area that is homogeneous. I want to have an area that allows my crack to develop, to get into a state that I understand, that I'm sure it's not affected by the initial nucleation, and then I want to see how this heterogeneity affects. The way it's chosen here is it should represent 50% of each material property. Okay, so the average is exactly the average of the two for this interface. Now, but the thinking behind is, so if you make an abstraction of the local mesoscale structure, we could say globally seen it's the average of the two. Now, let me show you the reference case, the uniform case, homogeneous reference case, SubRayleigh propagation in this case. We have here the crack, everything is intact. We have the crack that is propagating. Blue is basically open, bright blue is the cohesive zone. If you look in space, time, this is just output that is missing here. You see that the initial crack is accelerating initially. You see the cohesive, so this is shear corrections basically. The color, you see the cohesive zone here initially big, with the acceleration gets smaller and smaller and smaller, and actually you can see the bump. You can see the yellow, a little bit yellow area. That's the bump that actually allows you to get to super shear transition. And this is the graph you know already. It's actually the speed measurement of this particular simulation. Now, this was the homogeneous reference case. Now I show you two cases with the same material properties here, so the weak and the strong. In both cases, 50% weak, 50% strong. So the average is the same. Globally seen, it's the same behavior. And if you look now what's happening, you can see that it's propagating over here. It started, and then when it came, let me see if I can start it again. Yes, if it came close to the weak areas, the bump that is ahead causes this little dollar crack to be created in the weak area, and tries to pull the main crack to super shear transition, but isn't capable. As you can see, actually it separates again. So what you see in here is speed. This is the moment when it tries to put it to super shear, but it doesn't manage to, and then it stays in SubRayleigh. So the main front here is propagating in SubRayleigh, and you have these little pulses over here. They have very, very little slip. So I think experimentally you wouldn't even see that. It's so little slip. Now, if you look at the same case here with larger things, stripes, initially it starts the same way, but then there's this little dollar cracks in the weak area actually capable of pulling the main crack, and if you measure the speed, you're actually able to go to super shear transition. So if you look at here, the only difference between the two cases, macroscopically there is no difference, the same average behavior. Only locally we have here the stripes are actually 5 millimeters and here 8 millimeters, so a small difference, and you can have this extremely different behavior. And in terms of earthquakes, this is dramatic, because if this earthquake hits your house is going to be really bad. Whereas this one, it will have problems as well, but not as much as over there. Because here you have the Mach cone that hits your house, and here you don't have the Mach cone. And the last slide before the conclusion is, yeah, actually, that's why I said you can scale it down. There's a non-dimensional parameter. This is the width of the stripes, and this is the width of the cohesive zone. And you can determine this this non-dimensional parameter. And actually, process zone, linear elastic fraction mechanics determines that the bulk material, the shear modulus, affects it, the interface weakening as well. And this provides you a parameter that tells you which kind of propagation you have, and you actually can show it is valid. If you change one of the other parameters, you actually can have SubRayleigh behavior with the larger stripes, just because you manage to handle the correct thing. So with that, I want to conclude just saying that basically we showed that the length scales play an important role, and you can have something that macroscopically looks the same, but locally it's different, and the behavior that you observe, the propagation, is dramatically different. And so it plays an extremely important role.
Thank you.
Thank you.